Uh, okay, now it is being recorded. Okay, so we are talking about our screen. So we need to remove this trash which may get stuck in front of the screen sometimes. Normally we do it once in 24 hours or once in 48 hours. If we cannot let them accumulate it longer than 2 days because the contaminants which comes along with water, it may be an organic. So if it's an organic debris, so it may accumulate it and get degraded. And finally, this screen, this chamber may end up with some kind of smell generated. So every 1 or 2 days, we have to remove this trash. But anyway, it depends on the contaminants. During the wet seasons, a lot of flows coming, lots of waste discharging and come along with water, so that during the wet seasons, maybe the amount of touch will be really high. So the frequencies of screen cleaning may be once in every 12 hours. Sometimes it may be like that. So this uh, uh, mechanical equipment, we just use them to remove the trash from that screen. Uh, as I told you, they are the only one issue associated with the design of the screen, that is the head loss or the water difference between uh, the front and behind the screens. So if you really have a look at the screens, uh, if we locate the screens like this, so this is the chamber, and then if we located screens like this, normally it should be around 60 degrees to the horizontal, in between 45 to 60 degrees to the horizontal. So 45 it's maybe slightly small, but 60 would be the most appropriate. So water will flow through the screen. So I'm sharing uh, the screen right now, and hopefully you are seeing the OneNote applications. Okay, so this is the water levels. As I told you, if we put anything in the waterway, it's always creating some heat loss, just like a case of the pipeline. So if we reduce the surface area, oh sorry, the opening area, the velocities will increase. So increase of the velocities will finally increase the loss, and this loss will create the water levels difference between the front and behind the screen. So this is the flowless queue, and this is the directions of the flow. So water just passed to the screen to the opening area, and the water levels in front of the screen is given as probably H1, and the water levels after passing through the screen, it's given as the H2. So there are some uh, uh, difference between the water levels in the front and behind the screen. So if we apply the Bernoulli equations, so everyone knows the Bernoulli equations. So before entering to the screen, so water levels is given as the H1, and then the velocities heat may also generate it. So you have to include this term, V squared divided by 2G, and as this screens is open to the atmosphere, so before and after the pressure will be same, and they are the atmospheric pressure, so we don't have to consider the pressures. So after passing the screen at these positions, water levels after passing through the screen is given as h2, and of course the velocity passing through the screen is given as the VSC. So this one is the VSC, and this one is V. V is the approach velocities. This approach velocities, of course, equal to Q divided by the closed sectional areas. Velocity passing through the screens divided by 2g, and of course there might be some certain loss occur. Even the screen is clear, no trash accumulated at the front, there will be definitely the initial loss. Just imagine, so before entering the screen, the surface is given as A, which is equal to W into H. But at the position we install the screens, so some certain areas is lost as we put the bars here. So the areas, opening areas at the screens is of course smaller. This one is the opening areas for the screen, so it's smaller than the areas before passing through the screen. So even the screen is clear and clean, there are still some initial loss, because anything we put it in the waterway, there will be losses generated. Okay, so this is the Bernoulli's equations. So if you look for the water levels difference, which is equal to H1 minus H2, so this will be equal to the 1 divided by 2g, and we velocities to the screen minus the velocities, approach velocities. And of course, the loss must be there, but according to the calculations, the loss due to the screens, it's actually incorporated in a constant or a coefficient called the discharge coefficients. Normally, we use these coefficients to represent the amounts of loss generated due to the screens. So this coefficient is called the discharge coefficient. So discharge coefficient is put here. Uh, uh, Typically, discharge coefficients for the screen is 0.84. Okay, so discharge coefficient is actually coming from the loss, but water difference is there anyway. So this is something uh, 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 occur why we install something in the waterway, which caused the areas reductions. Okay, that is why this water levels difference becomes 1 divided by 2g. Sorry, this must be a c square. So if you are taking 0.8 square, you will definitely get a 0.7. And multiply by velocity to the screens and minus the velocities, approach velocities. That is why the water levels difference can be determined by using these relationships. So in the slides, you will find the water levels which may be created. It's equal to 1 divided by 0.7 v squared minus u squared divided by 2g. V is actually the velocities through the openings of the bar, and u is the approach velocities. So these equations we normally use to designs, not really designs, but uh, uh, we use these equations when we operate the screens. The issue associated with this screen is only the head loss after the operations. For sometimes the openings areas of the screens may get uh, clogged with debris or the trash, so that the areas of the screens, opening areas of these screens will even become smaller, uh, because some of the some certain amounts of the trash gets clogged in front of the screens. So if it gets clogging, these velocities to the screens will also increased. So if this amount increased, the water difference will increase accordingly. So after operations for some time, so how the water levels in the front and behind the screens will look like, there will be some more difference. So at the end of the operation, you will see something like this. Water levels in the front of the screens will increase while water levels behind the screens decreased. So that uh, this one, delta H, the difference is keep on increasing. So this is the only issue associated with the screens. And if we provide a kind of freeboards, water levels cannot be overflowing uh, uh, beyond these levels. So we may put some kind of sensors or some kind of the floating switch if the water level reach at these points. So this will give the command to the mechanical equipment to clean the screens. So something like this. This is called the mechanical screens. That is why the screen, it looks very simple, but somehow it requires a mechanical equipment, as you can see it in these photographs. Uh, uh, For the screens, we can actually classify based on the opening size. We can classify based on the configurations or the methods used to clean the entrapped materials. Or we can classify whether it is a fixed or moving screen surface. So these figures, we can say that this screen is probably the cost screens based on the opening size. For the smart screens, for the 5 screens, the opening size may be just a few millimeters. But for the cost screens, the opening size may be 1 centimeters, or it may be up to 5 centimeters opening areas, opening space. Configurations, we can say like this can be a just the bar screens or the drums screens or any other forms of the installations. Method of use to cleanse, whether it is the automatically cleaned or manually cleaned. So sometimes the operators, some kind of screens, the operator have to do it by themselves. That is the manually cleaning. So once a day, the operators have to remove the trash which may get entrapped by themselves. So that is the labor cleaning. But not the mechanical cleaning. So mechanical cleaning is just like the one that you have seen it in these figures. A fixed or moving screen surface. According to this photograph, this screen is just fixed. It's not moving. Unlike the drum screens, this is also a fixed screen. But okay, this one is the moving screen. like a drums. Water just get into the screen where this pipe, and water will enter the screens inside. So water will get inside the drums, and only liquids will pass through the opening areas which are around this drum. So there are some small hole around these drums. It's not actually the drums, but it looks like a conical shaped cylinder. So water just get inside and then pass through uh, the small space around this uh, 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 drum, and the trash we get entrapped inside. So this is a kind of the uh, moving screen. We can actually classify this one as the moving screens. And during the operation, this drum is always rotating. It's rotated all the time. So you can see that we have a cable connected this drum with the motor. So the rotational speed for this is in between 0.75 to 0.075 to 0.75 meters per second. The diameters, it depends on the size, it depends on the production capacities. So it may be just 0.8 meters, or it may be as large as 3 meters diameters. So these are a kind of the moving screen, but mostly the moving screen, they are the 5 screens or the standard. The standards is also the 5 screens, but uh, uh, this screen is just small, and this type of screen is not capable for a large production capacities, just only suitable for the small production capacities treatment plant. Sometimes we need to clean. So it's totally different from the previous figures. The mechanical equipment just removed by taking the trash and take them out from water and put it in the trash can. But for this one, as the trash get stuck inside, so in order to clean this screen, we usually provide a high pressure water jet. So high pressure water jet will be injected from outside, so that the trash will get stuck in the opening areas will be removed, and then we take them out from this site. So once a day, the operators may have to come and check, or even sometimes help these screens to remove the trash. The water jet may not be enough to 100% remove the trash accumulated inside. So this is a kind of this standard. And for the screens, as I told you, we classified it based on the opening size. 5 screen, a cost screens. Standard is actually the 5 screens, but the arrangement may be something different. Standard mostly refers to some screen which is very compact, and maybe something like this one. But for the 5 screen, so it's just a matter of the opening size. So if the size is very small, any small sized small opening size, we generally call a 5 screen. So it could be a fixed screen, or it could be a disc screens, some moving screens, dumb screens, like the like I showed you in the photographs. These are the beneficial use of the coast screen. Why we need to install these screens, because we want to protect the mechanical equipment, or the moving equipment from the big objects, or sometimes we need to use them to remove or prevent the aquatic organisms which may get inside or into these plants. For the water productions, we try to avoid having a kind of fish or shrimps presence inside our water treatment units. Otherwise, it may cause some kind of contaminations. And for the water productions, it must meet all the food and drink safety standards, safety guidelines, not just the WHO standard. So it's like we are producing something eatable. So just like a food industry, so they may need some kind of uh, 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 quarantine, like HAPP, HACP, or something. Water treatment plants also need that kind of certificates to ensure that all the production capacities, all the production process are quite satisfactory, so that the water produced from this plant can be consumed like that. So it's important. So it's important. Not just we are producing something supporting the communities, but this water needs to meet the requirements for food and for food safety. Uh, the locations for the cost screens, of course, in a water supply, a water treatment plant. So this the screens is normally set at the inlets of the surface water. So if you have chance to visit the treatment plant, you will definitely see the very first unit operations of this of all the plants is this screens. So it's there at the inlets of every water treatment plants. But in this semester, unfortunately, I've just checked with the programs. They still have policies not to allow the lecturers and the students, not to allow the lecturers bring the students for field visits. So this semester, unfortunately, maybe you will not be able to go for field visits. So you just have a look. The video clips I left it in the files. That is the plans we normally visited regularly. Every semester we visit there. So if you have chance to go, then you will see the screen is the very first unit of operation. The same as the wastewater treatment plant. The wastewater treatment plant is normally the screen is normally set before the pumping system, pumping facilities. But if there is no pumping facilities, the screen must be located before the primary sedimentation tanks or the grid chamber. This is another photographs of the screens with mechanical cleaning equipment. Alternatively, for the head loss other than the equation which we drawn it from the Bernoulli's equation. You can also use this uh, empirical formulas to evaluate, to determine the head loss. So the head loss is equal to beta. Beta is the shape factor. Beta is the shape factors. It depends on the bar types we used. So if we use the chap each rectangular bar, the betas, we need to take these values for the calculations to 0.42. And if we use the circular bar, we need this one, 1.79. We need to apply these shape factors for the calculations. The B is the maximum width of the bar. Small b is the minimum apertures or the clear spacings of the bar. But just be careful, as this is the empirical formulas. You need to apply the units corresponding to what they provided. So if it is the designates as meters, you have to convert everything into meters, even it's just few centimeters or few millimeters, like a kind of a clear etchings. But still, you need to whenever you calculate it by using this equation, the minimum apertures of the clear spacing, even it is very small, but we still have to apply meters, apply in terms of meters, not in other forms of the length measurements. VA is the approach velocities. Uh, Theta is the angles of inclination, 60 degrees or 45 degrees. So it depends on how we allocate the bar with respect to the horizontal. G, everyone knows that this is the accelerations due to gravity. And B, uh, beta, as I told you, is the bar shape factors. So you can also use this equation if or informations available corresponding to the parameters you need you want to apply into these equations. Otherwise, just used this equation, which is drawn it from the Bernoulli's equations. This is also good enough, actually. Whenever we design the mechanical equipments or any unit operations or unit processes, we need the criteria. So criteria is a kind of the suggestion uh, for the engineers to take this value. So you are supposed to take this value. So if you are taking this value, there's supposed not to be any problems occur later. But if you don't use this suggested value, maybe you will end up with some particular problems. But anyway, it depends on the situation. That is why this is a kind of the criteria. Criteria is not the standard. Criteria is not a regulation. So it's a kind of suggestion you can follow, or if you have meaningful reasons, maybe you don't have to follow. So it depends on the situations. But anyway, criteria is just a suggestion. So I'm sure that in civil engineering, there are thousands of criteria you have to apply it while designing the buildings or any forms of the structures. So for the screens, it's also same thing. This is probably the criteria, the design and operational criteria. So we have to pay attention on the velocities, and the other thing is the head loss when we design and operate the screens. For the velocities, the optimum velocities should be maintained at 0.6 meters per second. So the optimum velocities should be maintained at 0.6 meters per second. This is the velocities through the screen openings. Velocities through the screen opening. So what does it mean? So it means this amount, the velocities through the screen. So this actually should be 0.6 meters per second. So this is the optimum velocities. So if it's getting higher, what will happen? If it's like a 0.75 of 1 meters per second, what will happen? If we maintain at such a really high velocities, maybe there will be lots of force exerted on the bar or pushing the bar. So this will also not good. And finally, the entrapped materials can be pushed and then passing through the bar or being forced through the bar, and that will create the problems in the next unit operation. So we don't want that situations happen. That is why we don't maintain such a very high horizontal velocities, but minimum velocities we keep above 0.4 meters per second. Why we have to keep above 0.4? Because if we keep it like a 0.2 or 0.3 meters per second, some certain solid matter will precipitate or will deposit at the bottoms of the chamber. The same thing, we don't want this thing to happen because the next unit operations we will provide the facility to remove those solids anyway. That is why for the screens we don't want anything settled in the chamber. So there are not supposed to be anything accumulated at the bottoms of this chamber. That is why we keep the velocity to the screen as high as 0.6 meters per second, not 0.4 or smaller than 0.4. If it's getting smaller than 0.4, then there will be the depositions of the solids which we don't want. In terms of the operation, the head loss, initial head loss, I'm talking about the initial head loss or the head loss when the screen is basically clean. The initial head loss for the water treatments or the drinking water should be in the range of 0.05 to 0.15 meters or 5 to 15 centimeters, not that much high for the drinking water, but for the wastewater, it should be in the range of 0.1 to 0.4. So the range is getting larger for the sewerage or a wastewater treatment plant. Okay, so this is the initial loss. This is the initial loss. What happened? Why this application just come? I'm not sure. Okay, so this is the criteria. Okay. So talking about the minimum velocities, we should keep beyond 0.4. If we keep below a 0.4, that will be the deposition as I mentioned, but in the next unit operation. So we want all the grit, we want all the sand particles settled to the bottoms of the chamber. So in a grit chamber, you will find we prefer to have the horizontal velocity is just 0.3 because we want all the solids accumulated in that chamber. So the purpose are totally different between the screens and the next unit operations or the grid chamber. Okay, so examples of the calculation. So these are the question. You will be given the data, peak flow rate, Q. Just look at this conditions, this information. So here, just be noticed that we use the peak flow to design the screen. In fact, all the primary treatment, we need the peak flow. Okay, in order to design the primary treatment facilities, we need the peak flow. So in these questions, the peak flow is given as 80 million liter per day. Million, okay, million liter per day, not milliliters, million liters per day. 10 to the power of 6 liters, okay, million liters per day. The coast bar screen, we decided to allocate the bar like this. The bar, it's basically 1 centimeter width, and the clear spacing, it's another 5 centimeters. Okay, 1 is the bar and 5 is the clear spacings, and this bar is basically lie 60 degrees to horizontal, and the channel width is 0.75 meters. So what are you supposed to find out? You are supposed to determine the cross-sectional areas of the screen, the cross-sectional areas of the screen. So what should be the height, as the channel width is already given. So you have to determine the height. So if you know the height, just multiply the height by this 0.75, which is the channel width. You will definitely get the cross-sectional areas of the screens and also the minimum height accordingly. And at the end, if you want to evaluate the frequencies of cleaning, you can actually uh, uh, determine the head loss, and you can actually assume if the trash or the opening size get clocked for 50%, we will start cleaning like that. So this is a kind of frequencies of cleaning. So basically, we have to find out the head loss so that we will know at what frequencies we have to conduct the cleaning again, like that. So this is a kind of questions and the information that will be provided. In reality, you will also find this kind of question, but anyway, you have to decide. In fact, the size actually means the size determinations. Okay, the size in fact means the size determinations. So this is also the same thing. Whenever we talk about the size, it means that you have to finally come up with the number like what size should be the most appropriate. Okay, so this is a kind of example. So how do we begin with the cross-sectional areas of the screens determinations and the minimum size of the screens determinations? So question number 1 and question number 2. So how we should begin solving this equation, cross-sectional areas of the screens. First of all, you have to think about the how the screens look like. Okay, so I'm looking for the hot tea. So I don't know any of you like to drink tea. Mostly half Chinese or the Chinese people, they like to drink tea. This culture is actually originated from China, but it's spread all over the world. The tea, it's basically really popular in the Western country, especially in UK, and as they are really crazy to drink a tea in the afternoon. During that time, they present all the to the people who live in their empires to do the tea plantation. That is why now many other countries also have the tea cultures, and they also grow the tea, especially in South Asia, like India or Sri Lanka. These two countries also have lots of tea, but 10 years ago, so it becomes really popular amongst the Thai people as the some farmers, they have gained success in doing a tea plantation somewhere in the northern province of Thailand, but in fact the quality is not that good. I'm not sure about you, but as I observe, mostly the new generations, they like to drink coffee, not the tea. This also becoming a problems in Japan. Some of the people, they worry about the new generation, Japanese youngster. They don't like to drink green tea, which is actually the Japanese culture, the way to drink, the way to brew it. But nowadays, the mostly the youngsters, they just go to the coffee shops and order some coffee, just like what happened in Thailand. But as uh, for our country, we don't have a culture of drinking tea or coffee. So we begin with the coffee, that is fine, but some may begin with the drinking a tea, that is also fine. Uh, uh, in Taiwan, they also have lots of tea. So every time I visit this country, so I have to buy it, especially the oolong tea, which is also very good. But the tea in Thailand, the quality it's very good, but the way they are the manufacturers, it I'm not sure, but finally we don't get a good quality. At least not as good as some other countries made. In India, they also produce very good quality tea. Every time I go to India, so I have to buy some kilograms of the Assam tea back to Thailand. Luckily, there are some tea shops in the airports in Calcutta. India is also one of the countries that I visit very often, as it takes like only 2 hours flying from Bangkok to Calcutta. And if you want to go to the place like the Taj Mahal, you have to land it somewhere in Delhi or Jaipur. It takes like only 2 hours by train from these two cities to Accra, and you can do it like a one-day trips from the capital cities to visit the Taj Mahal. And from here to Delhi, so from Bangkok to Jaipur, it only takes 4 hours and 15 minutes by flights. It is very near, even very close to Bangkok, as compared to uh, other Asian countries like China or Japan, that we have to take at least 5 to 6 hours by flight. Okay, so uh, according to this example, so how do we determine the cross-sectional areas of the screens? So you have to begin with the concepts of if you are about to determine the areas, you have to think about the continuity equation. So in order to get the areas, you need to know the flow rates, and then you need to know the velocities. You need to know the velocities. So once you know the flow rates, and if you know the velocities, you will definitely get the areas. Areas is equal to the Q divided by Q divided by the velocities. Okay. So if you are taking Q divided by the velocities, you will get the area. Or if you are taking Q divided by velocities, you will get the areas. But for the screens, there are some certain criteria, as I mentioned. It's a suggested values for the engineers to use uh, for the designing the screens. If you want to determine the cross-sectional areas of the screens, we already have the criteria for the velocities. So the recommended velocities through the screen is 0.6 meters per second. It is 0.6 meters per second. So if you go back to the previous slides, the optimum velocity is 0.6 meters per second. Then you will be able to find the area. Okay. But just imagine how the screen look like. The screen is just installed like this. So this is the bottoms of the channel, and then this is the screen. This is water levels in front of the screens and behind the screen, and this is the flow rate. Flow rate is given as 80 milliliters per day. 80 milliliters per day. So 80 milliliters, it's basically 8,000 cubic meters per day, right? 80 million, 80, 10 to the power of 6 liters. And if you multiply by 10 to the power of minus 3, you will get in terms of cubic meters per day. And as the velocity is given as 0.6 meters per second. So you just convert this one into cubic meters per seconds by taking 80 million cubic meters, 80,000 cubic meters per day divided by 24 divided by 60 divided by 60 again, you will get the flow rate expressed in terms of cubic meters per second. Okay. So if you know this flow rates, you will finally get the areas. So the areas of the screen, the areas of the screens. Actually, this is just the opening area. Okay, A is just the opening area. So we are talking about only the areas that water passes through. Okay, so the areas that the water passing through is equal to Q divided by V. This amount divided by 0.6. So how much would you get? Square meters. Has anybody with the calculator right now? So can you just determine, just find out the value? Cubic meters per second. So all the engineers and even the engineering students has to be with calculators all the times. So calculator, it's somebody said that in the past, calculator, it's more or less like a weapons of the engineers, individual weapons for the engineers. So police are always with a gun. So engineers are always with the calculators. Without calculators, it cannot be a perfect engineers. Calculator, it's not an iPhone, so you need to be with the scientific calculators all the times. So you have to find this amount, and then you have to find this amount to get the opening areas. But once you already get the opening areas, you have to think about the actual configuration. This is the area of the screen, opening areas of the screen. This actually contains some bars, but the areas that we determine is just the opening area, which I put yellows here. A combination of all the yellows, it's equal to this amount. A combination of all the yellows is equal to this amount. But if you are about to determine, okay, this is a 60 degree. If you are about to determine the channel areas, which equal to the width into the depth. The width channel width is already given 0.75 meters. You're about to find out the height. You need to know the entire areas, but the areas you determine is just the opening areas passing to the screens. In order to get the actual areas of the channel, so anybody has some idea how we can get the actual areas of the channel? มีใครมีแนวคิดมั้งว่าจะได้ actual areas ยังไงดี and remember that this area whenever we talk about like Q equal to AV, Q is equal to AV, it means that this is the flow rate, like the velocity is given as a V, and the areas must be always perpendicular to the directions of the flow. So the areas you calculated, you obtained from this calculation is the area perpendicular to the flow direction, not the areas, not the inclined areas. Okay, this is the areas we determine, but not the inclined area. Do you have, but first, do you have any idea about how to obtain the actual area? Do you have any idea? Anybody has some idea? มีใครอยู่ในนี้มั้ง มีใครมีไอเดียมั้งฮะว่าจะหายังไงดี ข้อสอบมิดเทอมผมตรวจเสร็จแล้วนะฮะแต่ผมยังไม่อยากจะเผยแพร่คะแนน มีคนได้เยอะสุด46คะแนนจาก62คะแนน มีคนได้เยอะสุด46คะแนนจาก62คะแนน คนถัดไปได้40คะแนนนะฮะแต่คนได้น้อยที่สุดผมจำไม่ได้ว่าเท่าไหร่นะฮะตรวจเสร็จเมื่อสัปดาห์ก่อนโน้นละนะครับส่วนlab ผมยังกำลังจะตรวจนะฮะเพิ่งดาวน์โหลดออกมาแล้วก็ get the printout นะฮะเพราะว่านะฮะmaking a correction ในไฟล์ใน iPad เนี่ยมันช่าง complicate แล้วก็ not comfortable at all นะฮะwhile making a correction we don't just give a marks or give a points to the students, but sometimes we have to compare the other students answers. So if they are providing something same, they are theoretically speaking they should get the same points, but if they are doing something different, points may be different. So sometimes we have to compare the paper, and the only way to compare the paper, the best way to compare the paper is to get the printout. That is why, so I have to download and get the printouts for all 27, 28 copies. So just come to this question. So how do you have any idea how we can determine the actual areas based on the problems that I have just introduced? เราจะหาได้ยังไงฮะ area ตรงนี้ how do we determine the area มีใครพอจะมีไอเดียบ้าง มีใครพอจะมีไอเดียบ้าง ถามเป็นทีละบุคคลดีกว่า อันนี้เป็น critical thinking ล้วนๆเลยนะฮะมีใครมีไอเดียมั้งกันพิเศษอยู่ไหม
อยู่ครับผม
เราจะหา area ตรงนี้ยังไงดีในเมื่อตัวเลขที่เราได้เนี่ยมันเป็น area สีเหลืองๆมันไม่ใช่ area ที่แบบ excluding bar เนี่ยนะฮะเราจะหายังไงดีหายังไงฮะdo you understand about this one? This is 1 meters width and 5 centimeters clear spacing. So this is like a 1 centimeters width. The bar is 1 centimeters width. Clear spacing here 5 centimeters. เราจะหาได้ยังไงเมื่อกี้ใครนะ
หา area ทั้งหมดก่อนครับแล้วก็ไปลบบาร์สกรีนหรือเปล่าครับมันมีกี่อันนะครับ
ก็ไม่รู้ไงก็ไม่รู้ไงก็ไม่รู้ไงนะฮะเราจะทำยังไงดี
ไม่ทราบครับผม
มีใครมีไอเดียอย่างอื่นบ้างมีใครอยู่ในนี้อีกปรมาพรอยู่ไหมฮะปรมาพรอยู่ไหมครับนอนไปแล้วหรือว่าไงพดอยู่ไหมฮะ
อยู่ครับ
เราจะหา area ตรงนี้ยังไงดี
เราก็ต้องรู้ h ก่อนหรือเปล่าครับแต่ว่าไอตัว height
เราไม่รู้ไงเราต้องรู้ a ก่อนเราถึงหา height ได้ก็ height เราไม่รู้ area เราไม่รู้ตอนนี้เนี่ย
เราเอา flow ไปหาร velocity ก็ได้ area แล้วป่ะ
เอา flow มาหาร velocity เนี่ยนะมันก็จะได้ area ไอ้ตรงสีเหลืองๆนี่ไงเพราะไอ้ตัวนี้คือ velocity through the screen น่ะนะฮะคือ
เราต้องการคือทั้งหมดนะครับ
ไม่ใช่ทั้งหมดตรงนี้ผมกำลังพูดถึง area ไอ้ตรงที่มันอยู่ก่อนถึงสกรีนน่ะ area ของรางหาไงดีฮะ
ผมว่ายังไม่รู้เหมือนกันครับแต่ถ้าผมเดามันคือระยะ clear spacing หรือเปล่าครับไอที่เป็นคือมันมีแต่ละรางมันจะมี spacing ของมัน5 เซนติเมตรใช่ไหมครับ
ใช่
area มันไม่ใช่
คือเรามองไปด้านนี้สมมติว่าเรามองไปด้านนี้ area ตรงนี้ก็คือ area ว่างเปล่าแต่ตรงตำแหน่งที่เป็นตะแกรงเนี่ยมันก็จะมีไอ้เหล็กกั้นเป็นซี่
ครับซึ่งมันไอตัวเหล็กกั้นเนี่ยมัน1 เซนติเมตรทุกอันใช่ไหมครับ
ตัวเหล็กกว้าง1 เซนติเมตรแล้วก็ช่องว่างนี่คือ5ทุกอัน1 เซนติเมตรหมดเลย
1 เซนติเมตรกับ5ทีนี้เรารู้ได้ไงว่าตะแกรงมันมีกี่อันนะครับว่าแบบว่าไอตะแกรงของไอคอสบาร์สกีเนี่ยมันมีทั้งหมดกี่ช่อง
แล้วเราจะรู้ได้ไงว่ามันมีกี่ช่อง
วิด 0.75 เมตรเนี่ยเราก็เอา75ไปลบกับมันต้อง เราต้องหาไอตัว1 เซนติเมตรกับ5 เซนติเมตรรวมกันให้ได้75ใช่ไหมครับ
ใช่
เราก็ต้องมาหาก่อนว่าเราจะได้จำนวนตะแกรงกี่อันซึ่งผมก็ไม่รู้นะครับผมก็ไม่รู้ครับ
เหรอแต่อันนั้นก็งั้นคุณคงจะต้องใช้เวลาทำข้อนี้ประมาณครึ่งชั่วโมงSo this one is the areas that we obtained. This is just the openings area. So if you want to determine this area, these areas must be equal to this one. Multiply by 6 divided by 5. หมายความว่าไง So finally you will get the areas. One unit essentially consists of like the width is 6 centimeters, like 6 centimeters, 1 centimeters is occupied by the bar, and 5 centimeters is just the opening areas. Okay, so the entire areas, the ratio it's like this one 6, but the opening area is just only 5, and 1 is the ratio for the bar. So if you are getting this one, then you just multiply. You can simply multiply by 6 divided by 5, so you will get the areas, this area. And once you know this area, you can find out the height. So you don't have to concern about this value. Otherwise, it will be very complicated. So you can estimate the cross-sectional areas of the screen by taking this information. I will just look at the solution. So for the net areas of the screen's opening, here you are supposed to get 1.54. And this area you are supposed to get 1.848 square meters. And finally, you will get 1.848 divided by 0.75. So the height would be 2.464. So this would be the height of this screen. The height, this one is the height of the screen, and the areas of the screens is this one. Okay, so this is the entire areas, the cross-sectional areas of the screens. And finally, we get the areas of the screen, and then we also get the minimum height of the screen. But as I mentioned, whenever we determine the areas by taking this relationship, or it is an area perpendicular to the directions of a flow, it's the areas perpendicular to the directions of the flow. But in fact, our screen, it's 60 degrees to the horizontal. But the areas that we determine it's just a perpendicular area. So the height, if this is the water levels, so this is the height, 2.464 meters is the height. So if you really want to determine the length of the screen first, you have to take like this information, 2.464 divided by size 60, you will definitely get the length. So this length, you will get this one. Okay. And the same thing, if you are talking about the area, this area is also 1.848. So if you want to get the areas inclined, you should also take 1.848 divided by sine 60. It's the same thing. Okay, so this is about how we determine the size of the chamber. So now the width is 0.75 and the height is 2.464 meters. Remember that this is just a water height, water level's height. As the screen is not a swimming pool, so we need to leave some space here. So this space is normally called a freeboard. So water, it's just maybe 15 to 30 centimeters below the actual height of the chamber. So the space between the water levels and the actual height is normally called a freeboard. So this is just the water levels. So it's up to here. Whatever the values you determine, it is basically the water height, not the channel's height. If you want to leave some space just to prevent water overflowing or by accident water coming out from the channel or spill it over, so we have to leave some space, and this space is generally called a freeboard. Normally 1 feet or up to 50 centimeters. It depends on the types of the channels. It depends on the flow rates. It depends on the many other factors. Depends on the unit operation, types of the unit operations. But anyway, whatever the values that we obtained from the calculation is just only water width and height, not the actual channel size. So just to keep in mind. So if I ask you to decide, sometimes you have to leave some space for the freeboard. And the last questions, comments on the frequencies of cleaning. What does it mean? Comments on the frequencies of cleaning. The thing is, you have to imagine about the real situations for the screen. So after operated for some time, the trash may get entrapped in front of the screens. So if the trash gets stuck or clogged somewhere in front of the screen, so it will affect the opening space, as the opening space will reduced. So initially the opening area here it's 1.54 square meters. So this is the opening area. But if the trash, if the screen get clogged by a trash, the opening areas will definitely reduced. Normally, we'll clean whenever the area get clogged by 50%. So originally it was like a 1.54, but when it get clogged by 50%, so the areas reduced, the openings areas reduced by half, like this. So if the areas reduced by half, what will happen? you have to think about the relationships. A1 V1 is equal to A2 V2. So originally it was like a 1.54, and the velocity is 0.6. But once the opening area get clocked by 50%. So what will be the velocities? This will definitely increase double. So if the area is reduced by 50%, so instead of 0.6, so it becomes 1.2 meters per second. You can determine the initial loss. The initial loss can be determined by taking 1 divided by 2g, and of course divided by 0.7. This is 0.6, right? Square minus the approach velocities. With respect to the actual area, can you just find out the approach velocities? The approach velocities is, the velocities before entering to the screen. So you have to take Q divided by A again. The flow rates are the same, but the areas in this case, it must be 1.848. So this will be the velocities before entering through the screens. And finally, you will find this one. The velocities is 0.5 meters per second. So if you are taking the flow rates divided by 1.848, so you will get 0.5 square for the velocities before entering to the screens. So by taking these numbers, you will be able to find out the initial loss. And then once the screen get clocked, what will happen if it gets clocking lost will be equal to the same amount, but the only thing is the approach velocity is increased from 0.6 to 1.2 minus the velocities before entering the screen is the same because this area never get clocked. 1.2 minus 0.5 square. Then you will get the head loss when 50% of the areas we lost. Okay, so finally you can compare the initial loss and the head loss. The initial loss, this is the initial loss. But when the screen get clogged, water levels will increase, and behind the screen, water levels will decrease. So more loss you can expect it. Okay. This loss you can check again by taking a calculation. Okay. So we will clean when the head loss increase up to this value, meters or centimeters, I'm not sure. Okay, so this is how we solve this example, how we solve these questions. So finally, we can we have to clean the screen when the head loss reach this value. Okay, So we will clean the screen once the head loss reach this value, or we need to clean the screens once in every 48 hours or 24 hours, like that. So this is a kind of frequencies of the cleaning. The methods of cleaning, if it is the mechanical screens, mechanically clean screens, we will put the sensor. So once the head loss reach some certain levels, the cleaning procedure, the cleaning process will begin. But if sometimes the trash came along with the water, it's quite small. Uh, uh, Even 3 days, 4 days, head loss never reached the maximum value. Anyway, we don't wait for such a very long times because there might be some accumulation. But anyway, uh, uh, every 2 days, 48 hours, we have to clean them once. But this head loss just in case of if the objects, big floating materials come along with the water with a high amount. So we will pay attention on the head loss. But if the solid matter is lower, then we will be based on the time. So as I told you, once in 2 days, we need to clean the screens. Okay, so this is the answers to the last question. Comments on the frequencies of cleaning. Okay, so this is the first unit operation we have talked about as a part of the primary treatment. Then we just move to the other unit operation, which is also part of the primary treatment. That is the commit neuter. Commit neuter is basically the mechanical equipment equipped with several cutting teeth. As you can see it in this photographs, there are 3 set of the cutting teeth. This is actually nothing but just not really the equipment we use to separate solids from liquid, but these equipments we just use them to cut the big objects to a uniform size. Of course, the smaller size and also the uniform size, from big size to a smaller size, but uniforms. And then we let the next unit operation to remove these cutting objects from water. So that is the functions or how the commit neuters work. But anyway, as they are the mechanical equipment nowadays, this unit operation, this equipment may not be very popular. As the engineers, we are trying to avoid using the mechanical equipment. So we have to minimize the need to use the mechanical equipment as much as we can, because if we use too many equipments, we need to pay for the energy, we need to pay for the operations and maintenance, we need to take care all these equipments, and for the long run, so it will always creating some problems to the operators, so that the operators will sometimes get a headache, especially when the all these equipments are getting older. Lots of many parts that needs to be repaired. Sometimes we need to buy the new one. Okay, so this is a kind of mechanical equipment. We use them to cut the big objects to the smaller size, but not used them to separate any objects from water. If you really have a look at the plan view, you will find something like this. The cutting teeth are equipped here and here. According to the figures, there are only two sets of the cutting teeth, but in these figures, there are 3 sets of the cutting teeth. But anyway, water just flow through the channels like this, but once it reaches the comminutor, all the big objects are cut, and the liquid just pass through the comminutors to the to the bottoms of the chambers before passing to the other sides of the chamber. The comminutor is just equipped here. The problem with the comminutor is if we have like a heavy solid particles, there is a very high chance for these particles to accumulate it at the bottoms of this chamber. We use like a U shape to allow the water just passing through for the heavy particles just accumulated at the bottoms, so that we remove this accumulated objects by opening the drainage valves, so that all the trash can be removed. But of course, just only the heavy particles, heavy objects can be accumulated. For the light subjects, it may passing through these U shapes, and it is expected to be removed in the next unit operations. There are some certain advantages, although they are the mechanical equipment. We are trying to avoid using these equipments, but anyway, there are some certain advantages. We can eliminate some extra steps and some problems about the screens. But anyway, in some highly polluted water, many organic matters come along with water. Sometimes it comes like a big objects, so all this can be cut into a smaller size. Then we can handle them easily. But anyway, this is only suitable for the small treatment plant, not suitable for the large treatment plant. Just like a centrifuge, we use to separate the suspended solids from water, but the centrifuge, as they are the mechanical equipment, they are only suitable for the small treatment plants only. But these equipments also pose several disadvantages. You need to change the cutting tools after operation for some times, because as they are the steel, there must be some corrosion, and also as we have to make a U shape like this, there's very high chances of the organic accumulations at the bottoms if we are not handling them regularly or drain them regularly. It may cause like a unpleasant smell, or cause the conditions called the anaerobic digestions in this part of the chamber, which is actually not good. Okay, that is why we are trying to avoid using, especially for the larger plants. And nowadays, as I mentioned, for all the mechanical equipments, we are trying to minimize the need to use, we will look for other ways to handle the solid matter. Okay, these are the explanations how the commutator work. You can actually have a look at the figures. It is basically the same as I have just mentioned about it. Then we move to the next unit operation called the grid removal or the grid chamber. So what are the grid? Grid essentially refers to minute left granules like a sand or gravels. Mostly, this unit operation we use to remove all the particles which has the size larger than 0.2 millimeters, 0.2 millimeters, but they are basically the sand particles or it gravel. A grid mostly come along with the wastewater. In wastewater treatments, we will experience a lot of grit entering to the plant. So mostly we need to install these unit operations at the wastewater treatment plant. In water treatment plant, it may not be necessary, but it depends on the water supply sources. But probably wastewater treatment plant, especially the domestic wastewater treatment plant, require this equipment because grids mostly come from the activities like street washing, beach or sand, or the domestic sewage. So somehow we need to remove them first. If we don't remove grit or sands or gravels particles, what will happen? These particles may cause abrasion to the moving equipments like the pumps impellers or the mixing equipments in the coagulation and flocculation processes. Basically, this unit we use to separate solids from liquids. Okay, and this will help to reduce the formations of the heavy deposits in the pipeline of the channels. Just imagine that the sands and the gravels. So what are the specific gravities of sands and gravels? Generally speaking, it would be around 2.65, right? 2.65, which is about 2.65 times higher than the water. So when it gets into the water treatment system, so it will just deposit or it will just settle to the bottoms of the chambers anyway. So we need to remove them first to avoid them creating some problems in the next unit operation. So that is why we have to remove it. And of course, especially for the biological process in both aerations tanks and or even the digester, if we could remove sands and gravel, we can actually minimize the frequencies of cleaning. Cleaning the digester, it may be the operator may need to do it once in a year or once in 2 years. But if there are a number of sands and gravels particles entering to the digester, they may have to clean it more frequent. Otherwise, the activities of the microorganisms in the digester will drop, and then the operator will not get the treated will not get like the byproducts from the water and wastewater treatment. In fact, the digester, why we need to have the digester? The digester is actually the reactor carry out the anaerobic process, anaerobic digestion. The anaerobic digestion normally provide or yield methanes and carbon dioxide. And these methanes and carbon dioxide is we generally call it biogas, especially the methanes. It is the only gas produced from the biological process that actually has the calorific values, or we can use this methane gas as the energy sources for several purposes. So if we allowed thousands of sands and gravel particles entering to the digester, the activities of the microorganisms to produce the methane gas will drop. Finally, we will not get any methane from the digester. That will be the problems. Okay. So this is the major reasons why we need to have a grit removal. Okay, so from the grit chamber, so I just want to move to some slides. Okay, this one. This is the particle size classification. So it's basically somewhere several slides after this. Okay, so actually this slide it's somewhere in between the grit chambers and the coagulations and floculations. So I put this slide here. Okay, if you really take a look at the particle size for the grit particles, we expected to remove the particles with the size larger than 0.2 millimeters. So 0.2 millimeters is still the particle size which can be visible to the naked eyes. So for the size approximately 10 millimeters or the diameter approximately 1 centimeters, this is definitely gravel. But for some fine particles with the size around 10 to the power of minus 1 or 0.1 millimeters, this is a kind of fine sand particles or the precipitated forms of the metals. This size is still be visible to the naked eyes. So the grit chambers, we are aiming to remove this particle size. For the size larger than 0.2 millimeters. So if you compare when we drop these particles into the water, and then we allow them to settle 100 millimeters or approximately 10 centimeters. So just 10 centimeters. These particles will travel for 10 centimeters vertically due to the gravitational attraction. And we are assuming that the specific gravities of these particles is they are all the same, which is equal to 2.65. So for the 10 centimeters only, if the particle size is 1 millimeters or 10 millimeters, it will take 0.1 second to reach 10 centimeters in the vertical directions. But if our particles is as small as 0.1 millimeters, in that case, it may take like 13 seconds to reach 10 centimeters marker points. When we talk about the pathogen, the bacterial cells, phytoplanktons, or some small organisms. So their size are very small. Okay, it's even smaller than the gravels, sand particles, and other types of the mineral substance. So there are the 5 particles. So just look at the size. So this one is 10 to the power of minus 3, but it's 10 to the power of minus 3 of millimeters. Or in terms of meters, it could be a 10 to the power of minus 6. So these are the micro-sized. 10 to the power of minus 6 is the micron. So normally these particles we generally call the micro-sized particles. For example, the bacteria that we have to view under the microscope. So these are the microorganisms. We call them the microorganisms. Why we call them microorganisms? Because their size are very small. It's the micron sized. So you need to use the camera microscope to view. Otherwise, you will not be able to see how it look like. For these particles, it may take like 20 hours. 20 hours is calculated based on the specific gravities of 2.65, not approximately 1 like water. Okay. So other particles are very small. Colloidal particles 10 to the power of minus 5 millimeter or 10 to the power of minus 6 millimeters. So these are the colloidal particles. So these colloidal particles may come from mineral substance or may come from the precipitated products. Their size are very small, cannot be visible by our naked eyes. For the colloidal particles, 10 to the power of minus 6 millimeters means 10 to the power of minus 9 meters, or the nano sized. Okay, for the nano size, it takes 2 to 20 years. 2 to 20 years to settle with the vertical distance just only 10 centimeters or 100 millimeters. Okay, so now you can figure out how small is this particles we have in our water sample. Okay, that is why we have to come back again to the grid chamber. So grid chamber, it's basically we use to remove the grid. Okay, and the grid, as their size are very small, the densities are also quite high, quite large. So when we drop these particles, so it will precipitate it or settle to the bottoms of the chamber smoothly and flowing under the laminar flow conditions. Stokes formula STOKE, not STROKE, not this one. If you are talking about this one, this might be refers to a kind of disease, and many Thai people are suffering the stroke. It's a kind of something gets blocked in the blood vein, especially in the brain. So mostly the people who suffer from the stroke are basically cannot control the movement by themselves. So it's really the problems. So this one, it should be Stokes formula, STOKE, not STROKE. So there is something, there are some mistake here, mistyping. So the particles just dropped it in a water and flowing under the laminar flow conditions, and it drops and settles to the bottoms freely. That is why we call this particle will settle based on a concept of the free settling particle, the free settling particles. Okay. Concentrations of the grid particles are generally low. I mean, we have several particles, but they are not disturbing each other. Sedimentation of this particle to the bottoms of the chamber never been influenced by other particles. So each particles settle separately under the free settling condition, and they behave as a discrete particles, unlike the flux particles. The flux is originated from small colloidal particles which has or is surrounded by a negative charge. So theoretically speaking, these two particles cannot come in close together because the electrostatic force is very high until we add some kind of positive charge ion into water. Most of the positive charge ion are alum, iron, like this. And once we add these chemicals, add these metals, what will happen? All the positive, all the negative charge will be automatically neutralized. And once they are neutralized, these particles becomes can actually get closer and then becomes heavier, and finally they can precipitate or settle to the bottoms of the sedimentation tank. So this is a kind of particles settled to the bottoms of the chamber, but not the discrete particle. These are not the discrete particles. So discrete particles means the particles that they can actually settle to the bottoms by themselves without influencing other. Okay, so each individual particles just move down to the bottoms of the chamber, just only that for the free settling particles, and they basically behave like a discrete particles are settling. For grit sedimentations due to the gravity, sedimentations of the grit from water to the bottoms of the chambers. This process must be accomplished by the only the gravitational force. And if you want to determine the velocities of the particles moving in water under the gravity attractions, you have to determine by using the Stokes formulas. This is the Stokes formulas. Settling velocities is equal to accelerations due to the gravities multiplied by the difference between the densities of solids and liquids. The unit is kilograms per cubic meters, so don't make a mistake why okay. Settling velocity. So these are the difference between the densities of the solids and liquids. And this is the diameters of the particles divided by dynamic viscosities of the fluids. Okay, so this is the settling velocities of the particles in water. Okay, in water. That is why we consider the densities of the solids and the liquid. If you, as I told you in the beginning, grid chamber, we decided to remove the particles with whatever the size larger than 0.2 millimeters. So if you are allowed to design the grid chambers for the diameters of 0.2 millimeters, so can you find out the settling velocities? If the diameters is 0.2 millimeters, and then densities of the solids, you may apply, you may put 2,650 kilograms per cubic meters. The densities of liquids, you may try 1000 kilograms per cubic meters. And then for the viscosities of the liquids, viscosities of the liquids is basically the physical characteristic of liquids, physical properties of liquids. You can find out from the appendix of the or of the any hydraulic engineering textbook or the fluids mechanics textbook. Behind they usually are the physical properties of water information. So viscosities of the liquids vary depending on the temperature. So just check the temperatures, then get the viscosities of the liquids and substitute it into this equation. You will get the settling velocities. It looks complicated. This equation is normally called the Stokes formulas. It looks complicated, but actually it's not complicated. It's drawn from the force balanced equations. Okay, so this equation is drawn from the force balanced equations. So how do we obtain this equation? So you can just go forward to this slide. Okay, this one, not this one. Next, in the sedimentation. Okay, so this is a kind of, how do we obtain the settling velocities of the particles by concerning the force balance acting, the forces acting on the particulate matters in water. There are basically three types of forces acting on the particles in water. We all know that the particles has its own weight, W, and any forms of the objects present in liquids, there must be buoyancy force acting on these objects, and its magnitude is equal to the weight of the displaced fluid. Other forces acting on these objects in while moving in water is the drag force. Drag force is a kind of force which try to hold the objects while moving in the liquids or in even in the air or any forms of the fluids. Air is also fluids. Okay, water is also a fluids, but air is the compressible fluid. Water is uncompressible fluid. As you are the civil engineering, you don't have a chance to study the compressible fluids, but you only focus on the water, which is the uncompressible fluids. Drag force, we all know that the aviation industry, they make use of this drag force, because this drag force will help the planes flying into the sky. When we drop the objects in the air or in water, the drag force will always try to hold the objects. Like I will just show you, if I drop the paper, suppose this is the paper. So if I drop this paper, so there is a kind of, drag force trying to hold these objects. And the magnitudes of the drag force depending on the frontal areas. So if this paper moving like this, the frontal area perpendicular to the directions of the flow, so it's the square, right? So if I drop this paper, this is the frontal area. But if I change the way to drop this paper, so if I drop it like this, the frontal area is just very small. So the magnitudes of the drag force are totally different. So if I drop like this, the magnitude of the drag force is higher. But if I drop it like this, magnitude of drag force is very small or maybe negligible. Okay. Anyway, the same as the objects when they drop it into the water. So three forces are acting, and these are the magnitudes of the force we can calculate it. Gravitational force W is equal to mg. M is the mass. Mass is equal to the just remember that mass divided by V, M divided by V is equal to the densities. So if you want to know the mass, you have to take the volumes into the densities. The densities of the objects is given as the low one, and then as the particles is basically the spherical shapes. So the volumes of the sphere is 4 over 3 pi r to the power of 3, like this. And finally, you will get this forms, this term. This is the magnitudes of the gravitational force. And for the buoyancy force is equal to the weight of the displaced fluid. It's the same concept by determining the weight, but just change. We have to apply the densities of water, not the densities of the sphere, because we are focusing only on the weight of the displaced fluid, so that you can find out the magnitudes of the buoyancy force in this case. For the drag force is equal to this one. The magnitudes of the drag force depends on the frontal areas of the sphere. Just imagine about the sphere when we dropped them in water. The frontal area is just the circle, right? Which is equal to pi d squared divided by 4. If I'm holding this paper, the frontal area is width into length. But if I drop it like this, the frontal area is just a line, really small. So you can find out the magnitudes of the drag force. You have to consider the drag coefficients. You have to take the settling velocities, particles velocities into account to determine the drag force. And with respect to these figures, these three forces acting on these particles, so it's create the conditions as per the Newton's three laws of motion. Summations of all three forces is equal to mass into the accelerations ma, and the three forces are which are buoyancy force and the drag force. So the accelerations is the derivatives of the velocities with respect to time. Okay, and as for the particles, when it drops or get into the water, so it will try to move to the bottom with the constant velocities. Constant velocities means no change in terms of the velocities once it already reached the steady states. So the terminal velocities will remain constant. So if the terminal velocity remain a constant, it means that there are no changes. So dv by dt must be equal to 0 under this condition. So we are trying to find out the conditions so that we can obtain the solution. So finally, three forces are again combinations of these three forces are equal to 0. So based on this, just substitute all the values in the previous slides into this equation. You will get this relationship. And if you rearrange, you will get this one. Further arrangement, you will end up with this one. We settling velocities into the 4/3. Low one is the densities of the solids. Lower is the densities of the liquids. GD divided by CD. CD is the coefficient of drag. CD is the coefficient of drag. Okay. This is the general equation we use to determine the settling velocity. Vs is equal to 4/3. The difference between the solid densities and water densities. This is the general equations. CD is the coefficient of drag. Now you can see this equation is somehow a little bit more complicated. But if you want to determine the CD, so how do you find out? You can visit the chart called the coefficients of drag versus the Reynolds number. CD is the functions of the Reynolds number. The coefficients of drag is the functions of the Reynolds number. So I'm not sure whether you still remember the Reynolds numbers or not, but I'm sure that these topics, these contents, the contents about the Reynolds number, it's already studied once you are doing the second year studies here, because in the fluids mechanics labs, there is one lab called the Reynolds number. You have to find out the Reynolds number while the water flowing through the pipe. This one is also similar. The movement of the Reynolds number will change according to the flow pattern. So for the laminar flow, the Reynolds number, as the Reynolds number increased, the coefficients of drag will decrease. But for the turbulence, just look at the green line, so the spherical shapes. You will find if the Reynolds number is higher than 14, you can expect the spherical shapes we have coefficient of drag somewhere a constant. Okay. For the laminar flow, you can determine the coefficients of drag once you know the Reynolds number, and the Reynolds number it's given as low VSD divided by kinematic viscosities, or the settling velocities into a diameters divided by kinematic viscosities. So this is the way we determine the Reynolds number. Okay. But for the laminar conditions, the higher Reynolds number will be the lower coefficients of drag. For the transitions, it's in between, but for the turbulence, I think for the spherical shapes, so it must be around less than 1, and it tends to be constant, even though the Reynolds number gets higher and higher. If you study further, you will find that the laminar flow, which the Reynolds number is less than 1, you will find the relationships between the coefficients of drag and the Reynolds number, in which the coefficients of drag is equal to 24 divided by Reynolds number. So if you substitute these coefficients of drag, CD is equal to 24 divided by Reynolds number. So what are the Reynolds number? So how do we obtain the Reynolds number? Okay, here you can find out. And for the green line as spherical shapes, the coefficients of drag is equal to 24 divided by Reynolds number. Remember that the Reynolds number is this amount. It is this amount. Divided by 24, you will get the coefficients of drag. So if we know, like, if we know this information, you can substitute the Reynolds number into the previous equations. And finally, you will get the settling velocity is equal to GD squared multiplied by the difference between the densities of liquids and the densities of the solids, and again divided by 18 into the dynamic viscosities. So this is generally called the Stokes laws or the Stokes formulas. It's not complicated, but he's the one who initiated these equations. Okay, so this is the kind of how do we obtain this equation. So as a homework, you can actually find out what will be the settling velocities of the particles with the size 0.2 millimeters. So if you really find out, then you can determine the settling velocities accordingly. Okay, so this is how we determine the settling velocities. And in fact, the sedimentations of the particles occur in several unit operations and unit processes. We can actually classify it into 4 types of settling. Discrete particle settling is considered as the type 1. So for the grid settle to the bottoms of the chamber, and we have like a discrete particle settling, we will classify it as the type 1. So type 1 settling normally occur in the grid chamber. Type 1 settling normally occur in a grid chamber. And then type 2. So type 2 will be something like this: small particles, fine particles. Once they get surface modification characteristic, the charge around the surface become neutralized. These fine particles we get attached to each other again, becomes a heavier particles, and then we will allow them to settle in the sedimentation tank. So this process will occur in the this kind of sedimentation will occur in the coagulations, floculations, and also, of course, the secondary sedimentation tank. Type 3 is the hinder or zone settling. Hinder or zone settlings is just like a we are having a large number of the particles settled to the bottoms of the chamber. Suppose this is the flow diagrams of the water treatment. Begins with the screen and then followed by the grid chamber, followed by the primary sedimentation tank, and then we provide the agitation, rapid and a slow mixing tank. And after that, okay, so we provide secondary sedimentation tank again. This is rapid. This is slow. Okay, this is the sedimentation tank, and then filter, and probably chlorine disinfections. Okay, so for this one, type 1 settling will occur in here. This is the grid chamber. Part of the particles may settle in the primary sedimentation tank. And in this primary sedimentation tank, you can expect it to see type 1. But type 2 is the flocculant settling. Type 2 will basically occur in sedimentation tanks, in the settling zones in the sedimentation tanks. Here will occur in the settling zones in the sedimentation tanks. And type 3 is the hinder zones settlings. So this will occur in the bottoms of the sedimentation tank. But the last one, the concentrations of the particles is quite high. Most of the particles get compacted. So just settle to the bottoms all together. And then water is just like becoming squeezed, just like when we squeeze the cloths after washing, after laundering, then water just try to escape it from this particle. So this kind of settling normally called compression settling. Usually compression settling never presents or never exists in a series of water treatments unit operations or wastewater treatments unit operations or processes. But this will occur only in the sludge treatment, in a thickener, in a sludge thickener. In a sludge thickener. This will only happen in the sludge thickener, but it will not happen in any of these unit operation. The sludge thickener, what is the sludge thickener? The sludge thickener is actually the unit operation that we apply. We only take the particle settling at the bottoms of the chamber and put into this containers again. So this one is called a sludge thickener. And the compression settings will only occur in this sludge thickener, not in any of this unit operation. Okay, so we have 4 types of settling. So there are grid chambers only occur, only type 1 occur. Okay, so this is the photographs of the grid chamber. Basically, it's just the rectangular chamber. I think okay, so now it is about the 12 o'clock เดี๋ยวนะแป๊บหนึ่งนะฮะผมว่าจะขอเบรกไปอันนี้แป๊บหนึ่งกินน้ำนะฮะแป๊บหนึ่งนะฮะรู้สึกว่าน้ำมันหมดละเดี๋ยวเขาไปชงน้ำร้อนแป๊บหนึ่งนะฮะมันเหลืออีก30 นาทีกำลังจะคิดไว้ ยังไงดีนะจะยุติเลยหรือว่า นะแต่ว่า
อาจาร
มัน
ย์
ก็เล
อาย จารย์เบรกเลยก็ได้ครับ เบรกจนแลบเลยครับ
อะไรนะ
อาจารย์เบรกจนแลบเลยก็ได้นะครับ
ยัง
น่าจะหิวข้าวกันหมดแล้ว
แล
ครับ
บวันนี้ผมจะเลิกเร็วนะฮะเพราะฉะนั้นเดี๋ยวเลคเชอร์เลยขอเต็มเวลาแล้วกันงั้นเดี๋ยวผมขอเบรกแป๊บเดียว5 นาทีนะไปล้างมือไปอะไรนิดหน่อยด้วย แล้วก็ชงน้ำร้อนแป๊บหนึ่งนะฮะแต่แลบวันนี้ผมว่าจะพยายามที่จะให้เสร็จเร็วนะครับขอเบรกประมาณสัก5 นาทีนะเที่ยงเดี๋ยวเรากลับมานักศึกษาก็ไปเบรกกันแล้วกันนะครับ Okay, so just continue. ผมนึกขึ้นได้ว่าผมมีสอบโปรเจกต์ของอาจารย์อุรุยาเที่ยงครึ่งนะไม่เป็นไรเดี๋ยวเอาตรงนี้ให้เสร็จก่อนนะครับกลุ่มไหนก็ไม่รู้ผมยังจำไม่ได้เลยของนักศึกษาอาจารย์อุรุยาตอนนี้มันเที่ยงละokay so just come back to the grid chamber so this is the how does it look? So basically, the grid chamber is just a rectangular chamber. So I'm talking about the conventional grid chamber. There are several types of the grid chambers we can use, but the conventional one is the constant velocity grid chamber. If we apply the air, so it becomes the aerated grid chamber. And sometimes we can use the circular types. So in case of the circular types, we normally call it circular grid chamber. It looks like this for the rectangular grid chamber. So water just flow through the grid chamber. Normally, we made like a two chamber. The reason why we make like a two chamber because if one it's out of order, we still have one chamber in operations, or sometimes we need to fix some equipment. We still have another chamber working. So for water and wastewater treatment, it's always like that. We normally need to provide at least two chambers. We never only use the single units for the treatments. As I told you, if we only have one unit and if there's something wrong, the community will not have water to be used, or they will not have any treatment facilities to purify the water. So that is the problems if we only have only one units in operation. That is why normally we provide at least two units. For the pumping facilities, minimum is 2, but normally we need 3 for a minimum. That is why, according to this figure, you will find 2 units operated in parallel. Water just get into the chamber like this, and then sedimentations will occur in the grid chamber. This is the grid. This is the sedimentation zones for the first chamber. This is the sedimentation zones for the another chamber. Basically, it's just the rectangular chamber, but they just make it like this to enhance the precipitation so that there will not be any grit accumulated at the edge of the chamber. So all the grit after settle will be put to accumulate it in the grid storage below. If you really have a look at these figures, you will find after the grid chamber, there will be some hydraulic equipment called the partial foam. Do you have any idea why we need to use this one? This is the plan view, and this is the side view. Do you have any idea why we need to use the partial foams? Have you ever seen this kind of partial foam? มีใครเคยเห็นไหมฮะไอลักษณะแบบอย่างเงี้ยมีใครเคยเห็นไหม partial foam นะฮะมีใครเคยเห็นไหมฮะเคยเห็นไหมฟูมไม่มีใครเคยเห็นบ้างหรือว่าไม่มีใครเคยเห็นเลยใน lab fluid ก็มีนะฮะ lab hydraulic ก็มีนะฮะthis is a kind of partial foams, but in the labs they call venturi. Okay, venturi. In the labs, mostly we call Venturi, but in reality, we usually call this one as the partial fume. But in the labs, the only cross-sectional areas are reduced, but mostly the actual fumes, not only just the cross-sectional areas, but they also make some slope at the bottoms of the chamber, so that the hydraulic jumps it's being created while water is flowing through these fumes. So what are the beneficial use of these fumes? We use this fume just to just to measure the flow rate. So after passing the grid chamber, the fume is installed right after the grid chamber. So the water levels before entering to the fumes and after passing through the fumes, we measure the water levels and then determine for the flow rate. So this is the beneficial use for these fumes. And in terms of the water treatment, sometimes we also add the coagulants here, because anyway, mixing is already occur at this point, so that we can actually add the alums or any forms of the coagulants here. In this case, we don't need the rapid mixing chambers, so we just add it here. So mixings occur already. Okay, so this is the second beneficial use of this fume. The plants, Mahasawat water treatment plants, if you go back and have a look at the video clips, you will find the hydraulic jumps somewhere in the clips. That is in the clips, you will find they add the chlorine, they add the alums, the points where they add, that is the place they create the hydraulic jumps, and they make the fumes like this. So as the engineers, they have to decide, so what should be the width and how they can make the slopes like this to create the jumps. Alternatively, after the flow passing, after the water containing grid passing the grid chamber, they can also use the proportional weir instead. They may use the fumes like this, or they can also use the proportional weir. Have you ever heard about the proportional weir? You may know about the weir, but the weir that you try to do it in the labs, in hydraulic labs, it's also the same thing. You measure the water levels to evaluate the flow rates and measure the actual flow rates. Then you compare. That is the labs, the objectives of the labs. Just compare the flow rates from the actual measurements and also from the calculations after measuring the water levels. But anyway, this proportional weir is something totally different. So proportional weir is equipped here. It's like a plate. Okay, this is the plate, weir plate, and this one is the plates. The opening area is just here, highlighted by the yellow. This is the opening area. So what is the beneficial use of this proportional weir? We call it proportional weir because here, if you really have a look at the size, opening size, so it's wide at the bottoms and then gets like a bottlenecks if the water levels get becomes higher. So what is the beneficial use of this proportional weir? So this weir will actually help to minimize the fluctuations of the flows. Before entering to the proportional weir, there may be some fluctuations, but after passing the proportional weir, this fluctuation will get minimized because in some treatment plant they don't have the storage. If we have the storage, it doesn't matter because the storage can actually regulate the flow. So we install the pumps and then we can actually maintain a constant flow rate when we supply the raw water to the secondary treatments. But before entering to the storage, there may be some fluctuations in the midterm exam equation. You were also determining the volumes of this storage. So the proportional way is used as a substitution for the storage, but just in case of if there is no a high variations, just some small variations, the proportional we can handle. In that case, we don't need the storage. Okay, so sometimes we use this one. So this is the beneficial use of the proportional weir. This is the aerated grid chamber. Aerated grid chamber, by the name, you can expect it to see some air bubble added inside. So we blow the air here. So the air, of course, according to the physical characteristics of the air, when we blow the air bubbles will try to move up to the surface. So when it moves up, it always creates the water movement inside the chambers like this. So it becomes like a spiral. So all the grid which suspended inside will be brought into the bottoms by the water movement inside this chamber. So finally, all the grit will be accumulated at the bottoms here. This is also a kind of the aerated grid chamber, but the flow is just coming in these directions and moved out in this direction. More or less, it's like a circular tides, but this is the square. But it is also the aerated grid chamber. But if you really look at these figures, this is more or less the horizontal aerated grid chamber. But this one is the vertical aerated grid chamber. Okay, so air, the flow is just getting in where the inlets and move it like this before getting out through the effluent pipe. So this is the another forms of the grid removal, aerated grid removal chambers. This is a vertical type, but this one is the horizontal types with a spiral roll flow. Okay, so just come back to these figures again. So how we evaluate the performance of the grid chamber? As we all know that the grid chamber, we decide to remove the particle with the size greater than 0.2 millimeters. We decide to remove the particle size greater than 0.2 millimeters. For the particle size larger than 0.2 millimeters, it's supposed to be 100% removable once it enters the settling zones in the grid chamber. This is the figures showing the settling zones in the grid chamber, conventional grid chamber, which occur in the rectangular chamber. This is the directions of the flow, and dashed line indicates the entrance to the settling zones, and another dashed line indicates the exits from the settling zone. So the settling zones is only here. Okay, this is the settling zones. The problem is the particles with the size 0.2 millimeters. 0.2 millimeters. Once it enters the settling zone at these positions, So these particles will move to the bottoms of the chambers and reach these positions. Finally, this is the trajectory lines or the lines showing the movement of these particles, which travel from these positions to this position. So finally, it's accumulated at the bottoms of the chamber. It reached the bottoms of the chamber. So it will not goes beyond the settling zones. This is, we can say that it is 100% removal. Okay. This trajectory lines is the resultant between the horizontal velocities and the settling velocities. That is why I'd like to ask you to determine the settling velocities of this particle. Suppose the density is 2,650 kilograms per cubic meters. You can find out the settling velocities. And for the viscosities, you can have a look at the physical properties of water. So any hydraulic engineering textbook or water and wastewater treatment textbook, even this one, if you look at the appendix, there is a kind of physical properties of water. So you can find out the viscosities of water as a function of the temperature. Okay, anyway, the trajectory line is the resultants between the settling velocities and the horizontal velocities. Just imagine about the particles. The particles, it wants to move down to the bottoms, and then the velocities of the particles settling to the bottoms is Vs. But on the other hand, as the water flowed horizontally, this with the velocities Vh, these particles also traveling along with the water. Somehow it also moves in this direction, and somehow it also moves into this direction. So the actual directions becomes like this as a resultance of the horizontal velocities and the settling velocities. So this is the critical, we call this trajectory lines as the critical trajectory lines. It is very interesting if you consider the particles with the size larger or the smaller than 0.2 millimeters. For the particle with the size larger than 0.2 millimeters, you can expect that the Vs could be higher. You can expect that the Vs could be higher, right? So if the Vs could be higher, so if the size larger than 0.2, if the size is larger than 0.2 millimeters, what will happen? You can expect it the higher Vs. So the trajectory lines will becomes like this. Horizontal velocities is the same, but settling velocity it's getting higher because the larger size will be heavier. So the settling velocities will be higher. So for larger size, it doesn't matter. So if even though it enter any positions in the entrance, so it will finally settle to the bottoms of the chamber. So if their size is larger. But the problem is what happened to the particle with the size smaller than 0.2 millimeters? The problem is if the size is smaller than 0.2 millimeters, some certain particles will settle, but some particles will not be removed within this distance out. So for the particle with the size smaller than 0.2 millimeters, what will happen to the size smaller than 0.2 millimeters? The settling velocity is very small. So if we consider the particles entering to the settling zones at this position, so how the trajectory lines will look like? So it will be something like this. It will be something like this. Horizontal velocities will be same, remain same, but the settling velocities is smaller than this one. Okay, so this particle will reach the bottom, but beyond the settling zones. Or on the other hand, we can say that this particle will not be settled. Okay, so this particle will not be settled in this chamber. So it will goes along with the water and leaving the chamber. So if the size is smaller than 0.2 millimeters, on the other hand, if you consider the other positions that these particles entering to this uh, grid chamber, so the same particles, if they enter the grid chamber at this position, okay, they are having Vs, a smaller Vs, but the horizontal velocities remain same. So if they enter to the settling zones at this position, so what will happen? So the trajectory line of these particles will be something like this. Okay, this is Vs and this is Vh. So this line and this line are parallel to each other because they are the same size particles. They are having the same settling velocities. They are having the same horizontal velocities. So these two lines are basically parallel to each other. But finally, these particles reach the bottoms of the chamber at this position, which is still within the settling zones. So it means that for the particles with the size smaller than 0.2 millimeters, they can be partially settled within the settling zones. But some certain amount will not be settled in the settling zones. It depends on at what position these particles will enter. So below this, all the particles will be settled in the sedimentation chamber, but higher than this position, so it will fall beyond the settling zones. So we can say that for the particles with the size smaller than 0.2 millimeters, there are some certain removal percentage. Okay, so this removal percentage is basically depends on the position where they enter to the settling zones. So if they enter any points in between the edge, the depth edge, they can be removed. But considering the total depth or the entire depth given as a capital H, there are some beyond this, they will not be settled. So we can actually estimate a percentage of removal, which will be equal to the ratio between small h and the capital H. On the other hand, based on the similarities of the triangle, if you determine the settling velocities of the particles with the size smaller than 0.2 millimeters, and then you compare with the settling velocities of the particles with the size 0.2 millimeters, you will get the ratio. And this ratio will also be equal to the percentage of the removal of the particles. Okay, so a percentage of the removal by this grid chamber can also be determined by comparing the settling velocities, especially for the particle size smaller than 0.2 millimeters with the particle size 0.2 millimeters. But if I'm asking about the for the particles with the size larger than 0.2 millimeters, so what will be the percentage of removal. The percentage of the removal will be always 100% because the size is larger than we designed. Okay, so this is the idea about the grid chamber, and then that is why. So I'll just check the time. เดี๋ยวนะแป๊บหนึ่งนะฮะ okay. So by the grid chamber, you will be able to see something like this. อันนี้มันอะไรของมัน this is the grid chamber. Rectangular grid chamber. Water level. Flow rate. And this is the settling velocities, and this is the horizontal velocity. This one is the width, and this one is the height, and the settling velocities with the length out. According to this relationship, what you will get. So based on Q is equal to AV, considering the horizontal velocities, the horizontal velocities will be equal to Q divided by perpendicular areas is W into H. Considering the settling velocities will be also equal to as Q is equal to AV. So if we are taking the settling velocities, the perpendicular area should be W into L, right? So this is the velocities. So perpendicular areas is the built into L. And they are the same Q, so that Vs into W into L will be equal to VH into W into H. This one gets cancelled. So finally, we get Vs divided by VH is equal to H divided by L. H is the depth. Okay. And then settling velocities is always 0.021. Horizontal velocities we usually maintain at 0.3. So we will get the ratio, it's about 14. We can actually say that L is approximately 14 times of the maximum depth. Okay. That is why in the next slides you get these relationships. But as the engineer, we have to consider for the safety factor. อ้าวอุ๊ยตายนะฮะยกเลิก meeting ยกเลิกนะฮะผมต่อเลยแล้วกันนะครับ เพิ่งเห็นนะฮะเดี๋ยวแป๊บหนึ่งนะokay. That is why we are taking 1.2 to 1.5 times, so that we prefer to make the length approximately longer than 18 times of the maximum depth. Okay, so this is the maximum depth. This is the depth, and this one is length. Length should be at least 18 times of the maximum height. Okay. So that is all for the grid chamber. And at the end, grid chambers, the objectives of the grid chamber, it's only for a grid remover, not for the organic remover. Although the organic substance may comes in solid forms, but anyway, the objectives of the grid chamber, it's only for the sands and gravel particles removal, not for the particular the organic compound. So if you want to remove the organic substance, probably we need another types of unit operation. And the things we need to pay attention is the how do we handle the grid chamber, because at the end, just like at the screen, we have to clean the screen regularly. For the grid chamber, it's also the same. Grid accumulated at the bottoms of the grid storage, we need to remove it regularly. Otherwise, it may cause some kind of degradations and presents a smell will comes if we don't handle properly. But anyway, grid chamber, it's also a must to have a unit operation. We cannot, sometimes we cannot avoid it. Most of the wastewater treatment plant need to have this one, especially the domestic wastewater treatment plant, because all forms of the grids may come along with the wastewater. For the examples, probably we will talk about it again next week. Okay. That's all for today's lectures. It's quite long, 3 hours, but in this afternoon, we'll meet again at 1:30. So this afternoon, we will talk about the BOD and the COD. Quiz will also start at 1:30. The same as we have done it before the midterm exams, and I would expect it to finish by 2:20. So because at 2:30 I really need to leave this office for other missions. Okay, do you have any other question? มีคำถามไหมครับ มีไหมฮะ